Today we're going to be talking about bonding, and more specifically we're going to be talking about simple ionic bonds and forming binary compounds. Binary compounds are compounds that are made of two elements. So what is a chemical bond anyway? Well, a chemical bond is an attraction between atoms that allows the formation of chemical substances that contain two or more atoms. This is going to be caused by an electrostatic force of attraction between opposite charges. More simply put, elements that are chemically bonded form compounds. So there are three major types of bonds that we have that occur between different elements. We have ionic bonds, we have covalent bonds, and we have metallic bonds. Ionic bonding is when you have a metal bonded to a non-metal. And electrons are actually going to be gained or lost by atoms from the transfer of electrons from the metal to the non-metal, and it's going to form ions. That's how it got the name ionic. In covalent bonding, this occurs between a non-metal and a non-metal. Electrons are going to neither be gained nor lost, but they're going to be shared between neighboring atoms, so the atom directly next to it. In metallic bonding, it's a bond between a metal and a non-metal. It's a little bit different between ionic and covalent because you have what's called a sea of electrons. So what's happening there is the outer electrons, or the valence electrons of the metals, are actually able to circulate between all of the atoms, not just the atom that's right next to it. So this is going to help account for metals' ability to conduct electricity and for other properties like their metallic luster. So remember that atoms form ions by gaining or losing electrons, and they're doing this to try to reach a stable octet. That octet, so they want 8 valence electrons. If they gain electrons, so they're gaining a negative charge, you would form a negative ion. That's called an anion. If you lose electrons, you're losing something negative, so you would have an overall positive charge, and so you'd form a cation. Ionic bonds form between ions of opposite charges. So you're not going to have a positively charged ion bond with a positively charged. A positive is always going to be bonding with a negative. The compound formed by an ionic bond is always going to be neutral. To form an ionic bond, the metal is going to transfer electrons to the non-metal, forming a cation and an anion that are going to be bonded to one another. So in our example down here, we have sodium and chlorine. So these blue circles with the E's in them, those are the valence electrons. So you can see sodium starts with 1 valence electron, chlorine starts with 7 valence electrons. Sodium is actually transferring one of its valence electrons to chlorine. So that's uncovering that 8 valence electrons in its inner shells to now be its valence electrons, and it's making chlorine have 8 valence electrons at this point. So we can show this by drawing Lewis dot structures. These are also called electron dot structures. These dot structures are a type of notation that's going to help us show the number of valence electron an atom has. So simple electron dot structures just show single elements that have the number of valence electrons. So we have sodium here, so we write Na for its symbol, and then sodium has 1 valence electron, so we draw that valence electron as 1 dot. Chlorine has 7 valence electrons, so we have to include 7 dots around chlorine. So to form an ionic bond, we know the metal transfers electrons to the non-metal. That's going to form a cation and an anion that are bonded to one another. And we can draw this in our notes by having an arrow pointed from that 1 valence electron on sodium going to the chlorine atom. So that's showing us that this 1 valence electron is now transferring over to the chlorine. Okay, we can't point the arrow in the opposite direction. So it always has to be going from to where it's actually going. All right, so an ionic bond is the electrostatic force that holds oppositely charged ions together. Now, an electrostatic force is the force between particles that's caused by their electrical charges. So if the two charges have the same sign, like a positive and a positive or a negative and a negative, the electrostatic force between them is going to be repulsive. They're going to repel. If they have a different sign, so a positive and a negative, the force between them is attractive. So you have a strong electrostatic force between the nucleus of an atom and the electrons. So they are going to be attractive. So these lines here, the curved and the straight lines, show the electrostatic lines of force. Most ionic compounds are called salts. But if they have oxygen as their anion, then we call them oxides. An ionic compound has a regular pattern, and it is a repeating pattern of attraction and organization, and this is called a crystalline lattice. So you can see here in our diagram of NaCl, or sodium chloride, that we have a regular repeating pattern, and it forms a nice structure that's very, very organized. Because of this lattice structure and the electrostatic force holding it together, ionic bonds are going to be very, very strong. So these compounds have a high melting point and high boiling points. So we've got quite a few ionic compounds here, and our melting points are noted in this column, and our boiling points are over here. Remember, these are in degrees Celsius, and just as a reference range, this is not an ionic compound. I'm going to draw just water. It's actually a covalent compound. We're going to talk more about it later. Water has a melting point of 0 degrees Celsius. Okay, and it has a boiling point of 100 degrees Celsius. So NaI, sodium iodide, has a melting point of 660 degrees Celsius. That's really high, especially compared to water. But look at its boiling point, 1304. Very, very high boiling point. And this is because the ionic bonds are so strong. So ionic compounds can be either in a solid state or they can be dissolved in water. When they're in their solid state, they do not conduct electricity, but when you dissolve them in water, they become electrical conductors. This is because the ion crystals actually separate. So you have this big salt crystal here, and when it dissolves in water, all these little particles here are water, okay? Your crystals are actually going to break apart. So you've got sodium now and chlorine. This guy's positively charged because he's transferred that electron. This guy is negatively charged because he's accepted the electron. And so you've got a lot of electrical charges kind of free floating in the water. So they actually do conduct electricity. When you dissolve salts in water, we call these solutions electrolytes. So the easiest ionic bonds happen when two atoms of opposite charges bond. So, for example, what we've been working with is sodium chloride. Na has a +1 charge, Cl has a -1 charge. So they cancel each other out. If we were to add 1 minus 1 or +1 minus 1, you would end up getting no charge or neutral charge. And that's what we want for ionic bonds. But what happens when the oxidation numbers aren't always opposite? Well, in this example down here, magnesium chloride, they can still bond, but we have to change the number of atoms that we have. So we have magnesium, which was a +2, and chlorine is a -1. So overall, we would still have a +1 charge. To get rid of this +1 charge, we would need to add another chlorine ion. And so then you would have +2 -1 -1 to get a neutral charge. So you need 2 chlorine atoms for every 1 magnesium. So we would end up having to write magnesium. We know that there are 1. And chlorine, we know that there are 2. because we use subscripts to show how many of each ion we have in order to make the overall charge 0. But we don't have to use the 1. 1 is implied, so we can just write MgCl2 for magnesium chloride. There's an easier way to do this though, and this is called the crisscross method. And in the crisscross method, we take the charge of one ion and that turns into the subscript for the other ion. So in this case, oxygen has a charge of -2. So we take just that numeric value, just the 2, we leave the negative in place, and we drag and drop so it becomes Li2. So Li now has a subscript of 2. Well, oxygen, you only need one of those, and we know this because we can take this 1 from lithium, drag and drop, and make it a 1. And it's an implied 1, so I'm not going to write it, but we know that it's there. Otherwise, we wouldn't have written the oxygen. So let's get a little bit of practice in. That's the best way to do it. So we have a +1 and a -2. So we want to make potassium sulfide. So we're going to crisscross our charges so we know what goes with what. So K is going to have a 2 attached, S is going to want to have a 1 attached. We always write the metal first. So we write K, 2, S, and it's an implied 1, so we don't have to write it. All right, the next example. So we have aluminum, which is a +3, and oxygen, which is a -2. So I'm going to crisscross. I always like to start over there. Okay, so I have aluminum is going to have a 2 attached to it. I leave that negative value there, but I take the number. So Al2. O3. So in this neutral compound now, I have 2 aluminum atoms and 3 oxygen atoms or ions. In the case of calcium and oxygen, we have 2 and 2. But we don't need to write Ca2O2. We don't need to write that, because the 2's cancel each other out. So for every 1 calcium, you just need 1 oxygen because they cancel each other so nicely. So we just need to write CaO. So this is calcium oxide. So what you've learned today is you've learned that ionic bonding involves the transfer of electrons from metal to a nonmetal, and that's going to form a cation and an anion. Ionic bonds are very strong, so the compounds have high melting points and high boiling points. We've learned that ionic compounds form a crystalline lattice, so when they're solid, they do not conduct electricity, but when they are dissolved in water, they do. And we've learned how to write the formula, and to do this for an ionic compound, you must first determine the charge, simplify it if you can, and then crisscross and drop to determine the subscripts.